In this video, we're going to be talking about modeling variation. Should be a pretty straightforward video, but be sure to ask questions if you have them directly to me. Be sure to take notes along the way with the video. Listen, write, and work along with me. All right, let's get started. The first type of variation we'll deal with is direct variation. And it simply says if two quantities, x and y, are related by an equation, right here, this is the example we're going to use for direct variation. So I would just say that direct variation in my notes, y equals kx, where k can't be 0, otherwise you would just have y equals 0. And we say that, and this is important, that y varies directly as x, or y is directly proportional to x. So translating those sentences, I would place this in my notes, right? Both of these into my notes, because later on in the word problems, you're going to see verbal descriptions, and you're going to have to translate that verbal description into something more equation looking. Okay, k is referred to as our constant of proportionality. So also get that into your notes, that k is your constant of proportionality. K behaves very much like slope. So we'll dive right in. The cost, C, of printing a magazine is proportional to the number of magazines printed. And if it says it's proportional, if it doesn't say anything other than that, then we're going to assume that we're talking about directly proportional. So we know we have this y equals kx. And now we got to translate, I think, from cost and number of copies, right? So we'll use n as number. So we're going to have c and n as our variables instead of x and y. And we need to figure out which one is x and which one is y. So let's take another read. It says that the cost, C, of printing a magazine is proportional. So if I took from the page before, and instead of C, I put this, y is directly proportional, C is proportional, then it seems to me that we have a C is equal to k times the number of copies, where C is equal to our cost and n is equal to the number of copies. And that's the hardest piece, is getting that correct. Now we have some information. We have a $50,000 cost, so we're going to put 50,000 over here is equal to k times 2,500. Now, if you want to know how much it would cost to print 3,300 copies, what we really need to know is what's k. But we have a solvable equation for k right here, so let's go ahead and solve it. I'm going to just tidy up the page here for a second. So just kind of erase some things and move some things, and keep in mind that the cost is in dollars. So we have 50,000, okay, originally, is equal to k times 2,500. So to solve for k, we're simply just going to divide by 2,500 on both sides, and we're going to get a k equal to 20. Now that I have the value of k, we can use this to rewrite our general equation. So the cost is equal to 20 times the number of copies. Now what do they want us to do? They want us to solve for a cost given 3,300 copies. So cost is equal to 20 times 3,300. And 20 times 3,300 is $66,000. So that's the cost, and that's the answer. And doesn't that make sense? 2,500 copies, $50,000, more copies, more money. That's about it. It's as difficult as this section gets. All we're going to do from here is just add in a couple of other ways that we could have variables be related. We could have, for instance, an inverse variation. So if the quantities x and y are related by the equation y equals k divided by x, and I really would prefer to write that as y is equal to k, and really emphasize that it's k divided by x, for some constant where, again, k is not going to be 0, otherwise y would be equal to 0. We say that y is inversely proportional to x, or that y varies inversely as x, excuse me. So you want to get this equation, and you want to get these two phrases into your notes, so that when you see this word phrasing in a problem, you can quickly convert over. So this next problem takes up a lot of space, but that's just because it takes a lot of space to explain what's going on. So we have this idea of Boyle's Law that states when a sample of gas is compressed at a constant temperature, the pressure of the gas is inversely proportional to the volume of the gas. So again, as I see this idea that pressure is inversely proportional to volume, I'm looking back at that last page. Y is inversely proportional to X sounds like I have this original setup, Y equals K over X. And so now who is my Y? It seems to be that pressure is acting like the Y. So I've just gone ahead and said that over here, pressure is going to be P, volume is going to be V, K, our constant of proportionality, of course, is always going to be just K. So let's take a look at what this looks like. I think that we're going to go with P is equal to K divided by V. And now what do we have? They give us a little bit of a supposition here. Suppose that the pressure of a sample of air that occupies this. Now the tricky piece is that 50 kPa, okay, I'm just going to read it like that. This is the actual pressure. And the reason I know that is that volume is three-dimensional, okay? Volume is 3D space. So I see that cubic meters, that's how I know that that's volume. Now it's tricky as a student to read that because I see the word pressure and then the next number I see is that volume measurement. The pressure is right here. This is volume. And now that I've made a mess, I'm going to just clean that all up. All right, just clean that up a little bit. So the kPa is actually referred to as kilopascal, and a quick search on the internet will help you realize that it's a common used unit for small purposes and used for like atmospheric pressure type measurement. Anyway, we have 0.106 cubic meters, and so that's going to go in for our volume. So instead of pressure, I'm going to write 50, and I'll omit the units, equals K, which I don't know, over the volume, which is 0.106, and again, omitting the units. And if I place this over 1, we just cross multiply and solve for K, which is pretty simple and straightforward. So we're going to get a value of K is equal to 5.3. Okay, so that is our constant of proportionality. And the first thing they asked me to do here was find the constant of proportionality. So we're all set. Now it says if the sample expands to a volume of this. That's the other reason, a little catch there. As you read the question, notice the volume is in cubic meters, and this was also in cubic meters. There's another little hint to you that that was the volume measurement. Find the new pressure. So if we're looking for pressure, we have P as the unknown, K is 5.3, and we're going to divide by 0.3. So we're going to get a pressure of about 17.667. I'm just going to go to 3 decimal places. And again, that's a pressure reading, so we'll put on the kilopascal unit. Okay, and maybe we even want to express this in about, right? It's not actually equal, so we'll give the little wavy equals. All right, so we have direct variation in an example, inverse variation in an example. So let's move on to joint variation. Joint variation is just going to be a way to involve more variables. So you'll have quantities x, y, and z. So you'll notice that there are 3 variables as opposed to 2 variables in a constant of proportionality. So you have x and y together over here. And so what we're going to say is that k is a non-zero, and we would say that z varies jointly as x and y, or z is jointly proportional to x and y. So I would grab this equation and these statements and put those in your notes. Then we'd also have like perhaps a different version where we have, and I'm going to rewrite it down here, z is equal to k, and then I'm going to write x over y like that. And so this is where you have sort of a blend where z is proportional to x, or notice again we dropped off that directly because it's just assumed. Z is directly proportional to x, and inversely proportional to y. So we took the best of both worlds. We had z is directly proportional to x, and z is inversely proportional to y. And when you put these two statements together, you get this. So obviously, these two statements and this into your notes. As a side note, I noticed this, and this is not just our class, this is just over and over after 15 years of teaching. I noticed that if you are writing actively in class and during the videos, of course, it's like a portable class, you tend to remember. My Spanish teacher in 7th grade said, if I write it, read it, and say it, I tend to remember it. So there's something about actively passing something that you're hearing onto paper that helps you understand things and remember them, right? So just watching and listening, even if you did it intently, it just does not do the trick. And again, this is cognitive science. Don't take my word for it. It's fact. I notice that I'm often writing more than anyone, hence I'm getting better at it, but you tend not to be. So the struggle on your part a lot of times is just students aren't taking active notes. So I can't help but just give you that observation and say that typically it's a lack of effort on your part that really is the issue with mathematics. A lot of people are quick to say math is confusing. It's not. It's really just a lack of effort and fortitude. You got to stay on it. You can't just walk away because it gets difficult. So do your part. All right, so we're into examples immediately. So P is directly proportional to W. So P is directly proportional to W. That's it. All right, how about 8? W is jointly proportional to M and N. Well, before we had Z is jointly proportional to X and Y. So instead of that, now we have W is jointly proportional to M and N. That's it. Number 10, P varies inversely as T. So before we had Y varies inversely as X. So now we have P varies inversely as T. For 12, we hear or say A is proportional to the square of T and inversely proportional to the cube of X. So we have A is proportional, and I heard inverse in there too, so I'm just going to get the inverse set up, is proportional to who? T, but the square of T. And inversely proportional to X, but the cube of X. Okay, not the cube root, not the square root, but the square and the cube. All right. For 14, we have S is jointly proportional. So S is jointly proportional. It means I know I have multiple letters coming to the squares of R and theta. So the squares of R and the square of theta. I suppose we could say that S is equal to jointly proportional to the squares of R and theta like that. But I think I like this one better. It's a little safer. And then for 16, we'll have two options. We have A is jointly proportional. So A equals K to the square roots of X and Y. So the square root of X and the square root of Y. Or we could have A is equal to K, X, Y. And according to the rules of exponents, that's why we have, and that's what radicals are, they're just exponents. Keep in mind that the square root of X is the same as X to the 1/2. So exponents and radicals are one and the same. The rules of exponents say that these two expressions are the same thing and that these two expressions are the same thing. So again, I think the primary versions that I wrote are the safer way to turn around and go back and mathematically apply arithmetic. But whatever floats your boat, I'll take both. So now we get into the application. And the first one we have here is Hooke's law. States that the force needed to keep a spring stretched X units, and its X units, the key word is beyond its natural length, is directly proportional to X. Here the constant of proportionality is called the spring constant. So first off, I'm going to say that K is equal to the spring constant. Now back up here, it says that the force needed, and then there's a bunch of wording. So force needed to keep a spring attached X units beyond its natural length is directly proportional. So force is directly proportional to X. So just a little note here that force is our y value, and x is measured in terms of number of units beyond its natural length. So let's use F for force. So we'll say that F is equal to our spring constant times x. Okay. So this would satisfy our answer for A above. Now B starts giving us some information. It says a spring has a natural length. So the natural length is 10 centimeters. And it also mentions that it's going to go from 10 centimeters and it's going to stretch to 15 centimeters. So 15 minus 10 is going to equal 5 centimeters. This is our value for x. That's the number of units beyond the natural length. Right? And it also said that it needed 40 newtons of force, right, to get there. So our F is equal to 40. And what we're going to need to do is to find the spring constant. So for B, what we have is 40 equals K times 5. And it's the 5. I'll put a little asterisk above that. That's the key piece. As you'll notice up here in the picture, they're trying to highlight that the natural length of the spring there versus the extended spring. Remember, x is only the difference of the natural and stretched version of the length. Okay, so obviously, if you divide by 5 on both sides, you're going to get a spring constant of 8. Now that we have our spring constant, we can easily land the answer for C by going back in and saying force is equal to 8 times x, where x is the natural. And it says what force is needed to keep the spring to a length of 14. Keep in mind that this is not 14. You have to subtract the 10 from that to get your answer. So go ahead and complete C on your own. Don't forget to include units for an answer. And the last one we have here is stopping distance. Right? The stopping distance, D, for a car after the brakes have been applied varies directly as the square of the speed. Okay, so let's see here. We have the stopping distance, D, of a car after brakes applied varies directly, so K times the square of the speed, so that's speed squared. Now, just so we're all on the same page, it would seem that the faster a car goes, the longer it takes to stop. So we should have, some idea about what is a reasonable answer, what's an unreasonable answer. And so they give us some information. They tell us that a car is traveling 50 miles an hour, can stop in 240 feet. What's the maximum speed it could be traveling if it needs to stop at 160 feet? So in between, this one doesn't really walk us through all the steps, but obviously we need to get a generic equation, then we need to solve for K, and then we're going to use that given info to answer the problem. Okay, so after squaring 50 and getting 2,500, I divide by 2,500 on both sides, and I get K is equal to 0.096. So I have a new setup, and my new setup is saying that the distance required to stop is equal to 0.096 times speed squared. Okay, now it says what's the maximum speed? Now if we're looking for maximum speed, I guess this is still going to just stay S. So what do I know? I must know the distance. If we're required to stop in 160 feet, then 0.096 times S squared is going to get us there. Looks like we got a quadratic. I'm going to divide by 0.096 on both sides and solve for S by taking the square root. So I've abbreviated here on my screen to 1,666 and 67/100ths. take the square root of both sides, I get S, but I'm actually taking the square root of the exact answer on my calculator screen, and I get, again, approximately 40.82, and this is speed, so we'll say miles per hour, right? And so I guess what they say, MI. So doesn't that make sense that if I have less speed or less space to stop than the 240, that I have to be going slower than 50, and about 10 miles slower seems to be at a reasonable speed. That's it. So it's just, what seems reasonable. All right. That'll do it for today. Hopefully this was helpful. I'll post the homework on Blackboard.